Good afternoon, everyone. Thanks a lot for having me here today, and thanks a lot for the organisers for this fantastic meeting. It's really good for us in universities to talk about some of the instruments we do and some of the things we're doing, because if we didn't have that sort of communication and collaboration with the industry, we'd probably be doing too much pie and sky research and not enough really dedicated real world projects to really help the local industry. So we've strived to do a lot of sort of applied research at Curtin University in general, but in specifically in the JdLC Centre. So we've been closely collaborating or closely affiliated with the WA School of Mines, where for a generation or so we've really done a lot of research and training of geoscientists and geologists in Western Australia. So I'll talk a little bit today about a broad sort of overarching capability of the centre, and then I'll hand over to my collaborators to talk a little bit more about some specific projects and some really interesting research that they're doing. Okay, so the JdLC Centre, so we're the centralised research infrastructure facility in the university, so similar to the CMCA. We were founded in the early 90s by John Laeter, and for those who know him, he was a real pioneer in mass spectrometry. He's done some really amazing things in the field, and that sort of legacy is sort of continued on in the centre. We have a real strength in mass spectrometry and geoscience, and we sort of have a number of staff, probably not as many as we need, but we've got a number, and a bunch of instruments across a number of different laboratories. And really what we're trying to do is have really world-class, state-of-the-art instrumentation, and then let people use it and do really good research. So that's students, and it's also industry. So that's what we're striving to do. So this is our facilities. So as I said, we're probably about just 10 minutes south of here, and mostly based in these two buildings, Building 301 and 312. So we've got a real sort of centralisation of a range of different labs, and you can see the labs that are sort of in this sort of reddish colour. They're all our mass spectrometry facilities, and so we do sort of ion microprobe, we do sort of noble gas work, laser ablation, all the way down to some more novel techniques such as atom probe tomography, TOF-SIMS, and a number of other things, which I'll talk a little bit. Well, I'll briefly skim over during this talk, and we'll get some more detail in the following talks, and also tomorrow for those coming on the tour. So we still do also some core sort of analytical techniques such as X-ray diffraction, microscopy, electron microscopy, and so forth. So we really have quite a wide suite, but really a strength in mass spectrometry. So we're a research centre, so we've been doing research for a long time, and so if you sort of put into sort of Google Scholar and try to look at how we've been performing, we've sort of written a lot of papers that sort of made a big impact in the scientific community over a long period of time. So we really sort of drive some core strengths of the university, being the geoscience. And when we sort of look in sort of scientists talk, the university is really highly ranked in geology and geochemistry. So we push that because that's our strength. Okay, what are those publications on? You can see some of these keywords. So if you sort of put it into one of those sort of word mining algorithms and pump out what are the things that we're usually talking about, and these are the things. And you can see zircon being front and square because we do a lot of geochronology, a lot of dating. We do process metallurgy and some ore exploration work as well, and you can see sort of a number of those relevant sort of keywords popping up. But we also like to talk about the fact that we've dated some of the oldest rocks on Earth and Mars and the Moon. So that's always a nice feather in our cap. So what do we provide? So we provide excuse me, research services. We support, so we conduct our own research projects. We also support other people's research projects. We're developing new methodologies, so we're being able to do things that weren't able to be done before, and one of them being sort of nanoscale geochronology, which I'll briefly touch on. But we do projects directly with industry, either as a research program or just a pure consultancy, and we train. So we run a number of training courses and different techniques, and people from industry and also students can attend them and learn a little bit. Okay, so it says here one-stop shop for geoscientists, but it's not exactly true. There's plenty of other things you can do that we don't have, but for a particular workflow we can do quite a range of different analyses. So we have some really nice sample preparation facilities, including this cell frag facility, so it's pulse differentiation facility, which effectively can break apart a rock on its grain boundaries, and we can separate specific minerals of interest for further analysis. So that's really neat, plus a range of sort of standard sample preparation techniques. And then from characterization we can move through microscopy to diffraction to laser ablation, all the way down to sort of atomic scale analysis with atom probe. And then geochronology, we can target a range of different isotope systems, and they're sort of relevant to different ore bodies and mineral types, and we can use our range of different mass spectrometers to target them. And also some trace element geochemistry, we can look at that. So all these different techniques, which one to use and why do you use it? So that's always a good question. That's why we got to have an open discussion about what you need and how you might do it. And so if you're looking, does this work? Sorry, you can't see can you see a pointer? No. Let's try this. Okay, so this figure here, you can see a whole bunch of different techniques, probably quite a few of them we have at Curtin University. So all the way down the smallest length scale at atom probe, and up to sort of dynamic SIMS, which is ion microprobe, X-ray diffraction, things like that. So we can target them depending on what sort of precision you need, what sort of scale are your features. And specifically in mass spectrometry, this really nice figure by my colleague Dennis Figueros, he sort of made a sort of schematic comparing the different structures within a grain, for instance a zircon with a sort of different microstructures, and if you analysed it with different techniques. So certain techniques will use more of the sample, so larger sort of analysis volume, all the way down to almost a negligible size analysis volume for atom probe, and that sort of gives us different spatial information, and it'll have different associated sensitivity. So the more you analyse, generally speaking, the more information you get and the better precision. So you can see ID TIMS, which basically you can dissolve a whole grain, you get amazingly precise data, whereas when you start using a small amount of material, and I haven't graphed it here, but if you looked at the error bars on an atom probe dating, it'd be much higher, but you're getting that date from a very specific region. So you change your analytical technique depending on what you're trying to find out and where you're trying to find it out from. So if you're targeting say a twin boundary or within an inclusion within a grain, then you'll have to choose your technique. So just briefly, so the shrimp, so it's sort of, as I mentioned before, JdLC Centre, JdLC himself really pioneered this technique, and it's been used over the last sort of 30 years in WA for dating, a whole bunch of things, and so much of the sort of geological maps of Western Australia really sort of owe a lot of their information from data collected in the JdLC Centre. And just for your information, this instrument is basically used almost 24 hours a day, 7 days a week, all year round, for decades. So this instrument's been pumping out data on geochronology for Western Australia for a very long time. A really fantastic technique, and it continues to do so. So it's really a stalwart of WA geoscience, really. But we are moving into some modern techniques as well. So laser ablation, ICP-MS, as you've heard in some of the other talks, it's really a interesting technique because of its speed. You can do automated analysis, and you can sort of see the sort of centres down the bottom. We can sort of date, you can get over almost 400 ages in a day, and you can do trace element maps. So we can really do fast automated analyses, and you can look at trace elements in in this particular application, we're looking at a lead-based filling and how that lead is diffused into a tooth. So we can use it for non-geoscience applications as well. But it's a really neat lab, and this one in particular is extremely busy, booked out months on end. So our core facilities in microscopy and microanalysis, we have a range of different techniques. So we can have just sort of your standard petrography, optical petrography techniques and light microscopes. We have a range of different scanning electron microscopes, all the way down to transmission electron microscopy. And then associated with particularly the electron microscopy techniques, we have our microanalysis techniques being energy dispersive spectroscopy and particular strength being electron backscatter diffraction. So we can do mineralogy inside an electron microscope, and we can link the structure to the composition. I'll just briefly mention this because this will be talked on more in a minute about TEMA. So this is a T-scan integrated mineral analyzer. So we can do automated mineral mapping, and that's been quite an interesting technique for us. So we can sort of look over a large area at the mineralogy. Okay, let me see if I can get this video going. Atom probe is a really exciting technique in the geoscience. It's really bringing sort of nanoscale analysis to big rocks. So we start with a big rock and eventually we come down to extracting a very small portion of that rock out, and we do at atomic scale 3D analysis. And from that we can look at nanoscale variations, which we can get important information about ore systems. We can look at how gold is coalescing into sort of nanoparticles, which eventually coalesce into larger particles that we can use we can see in ore deposits, and we can really see the genesis of some of these things. In this case here, we're looking at zinc sulfide ore, and we can see in this case here, it had this sort of segregation at a very, very fine structure, and we can study that structure to look at the reasons for that. And so this particular quote down the bottom is ability to collect geochemical data has outpaced our understanding of geological process. So basically our instruments have gotten really, really good. Now we've got to understand what the data means. So that's what we're working on. But already this instrument has produced a really number of high impact papers, so we are starting to understand what's happening at the nanoscale. And for the people coming for the tour tomorrow, you'll really see some really nice examples of what we're doing. And sort of on the similar theme to some of the earlier talks is we can really correlate our analysis by combining a bunch of different techniques. So we can start at the grain scale, we can analyse the chemistry and the microstructure with the various sort of techniques that we have, and we can do our imaging mass spectrometry, we can do our nanoscale sort of 3D analysis, and we can also do our nanoscale microstructure analysis with transmission electron microscopy. And we can, because we're using similar instruments co-located and some fancy workflows, we can really do some correlative studies. So we do have a couple of new bits of kit coming. So a new TOF SIMS instrument, so a real dedicated instrument for time of flight SIMS. Time of flight compared to sort of magnetic sector SIMS is basically we can get everything in one analysis. We don't have to target specific isotopes or masses, and so we can analyse 500 different masses at once at 50 nanometer spatial resolution and 30,000 mass resolution. And we have a new EBSD SEM system which can do really high precision analysis. So with that, I'll thank you.